Hey guys, let's go ahead and continue our discussion of rates. This is video 2.2.1, our 2.2 lesson, and today we're going to talk about the integrated rate law. So the integrated rate law is a really cool and easy visual way to see what the rate law is for your specific chemical reaction. So the integrated rate law describes the relationship between the concentration of the reactant and the time. So let's look first at a zero order reaction. We're going to look at zero first and second orders today. Okay, so consider the reaction A just goes to products. The rate law for this, as we know, if it's a zero order, will be rate equals K times the concentration of A to the 0th power. As the concentration of A decreases, the rate, or the slope, is going to be constant in this case. So is constant. So the rate, or the slope, is constant. And because you have a constant slope, that means that you are going to have a straight line. So the rate is going to be equal to the slope, which in this case is going to be negative K. It's negative because A is getting used up. A is getting used up. Okay, so sketch the concentration versus time graph to the right. So all it is a straight line. So I'm just going to sketch a straight line there. So let's point out a couple of important points on this graph. So this point here, the one actually on the y-axis, that's the concentration of A at time 0. So here's our time on the x, so that should make sense. So the concentration of A at time 0. This slope, m is for slope, remembering y equals mx plus b, your m is your slope, is going to be negative k. And it makes sense because that slope is negative. So that's your actual k value. Sketch the concentration versus time graph on the right. We did that. Write the equation of the graph in point-slope form. So we're going to be rewriting everything in point-slope form. So the first way I'm going to do it is in y equals mx plus b. So slope-intercept. Y equals mx plus b. Our y, in this case, is A, concentration of A, at some time t, whatever time t you're interested in, equals, and then m was our negative k, so negative k, x is your time, x-axis is time, plus your y-intercept here is A at time 0, plus A at time 0. If we're going to rearrange this into slope-intercept form, we would get concentration of A at time t minus the concentration of A at time 0, or the initial concentration, is equal to negative kT. Now, it's important to note that this equation is a very useful equation, and it's not provided to you on the AP equation sheet. So not provided on AP equation sheet. Therefore, I strongly recommend that you memorize this. Memorize this equation. All the other equations you're going to get today are provided to you on the AP equations sheet, so it shouldn't be too bad to memorize this one. So let's go ahead and define our variables here, just in case we're not sure. So the concentration of A at time 0, or A sub 0, means concentration of A at time 0, or initial concentration. Concentration of A sub t equals the concentration of A at whatever time you're interested in, t. Anything other than 0 at that point. Okay, so that's zero order reaction. First order reaction gets a little bit different. So we are going to consider our reaction here. A goes to products again, and this time I'm going to tell you it's first order. So the rate law for a first order reaction is rate equals K times the concentration of A to the first power, because it's first order. Here, as the concentration of A decreases, the rate, or the slope, also decreases. So this is a reaction that's slowing down over time. It starts off really fast, and then it starts to slow down. So as we would expect, we would get a curve for this, for our concentration versus time graph. So we should get a curve. So as the rate gets slower, slope gets smaller, so we get a curve. And we sketch that over there already. That's our curve. Unlike the zero order reaction, the concentration versus time graph that we've drawn here is not very useful. And that's because it's not a straight line. So we can't really write the equation of that line over here, and we can't use it to make predictions about this reaction, which is really what we need. So it's not useful because it is a straight line. Or sorry, it is not a straight line. It is not a straight line. So it is not useful for analysis. So really here we want to get a straight line. So what we can do is just take the natural logarithm of everything. So ln, natural log, if we take that of everything, we end up getting a straight line. So for a first order reaction, we get a linear relationship, which is what we want, between ln of a, natural log of a, and time. And the slope here, again, is m equals negative k. Write the equation of the graph in point-slope form. So we're going to do the exact same thing as before. So I'm going to go ahead and draw my straight line first, so we can kind of just get a visual for where everything is coming from. So here, the difference between this and the 0th order reaction is now we have natural log of A, versus before we just had pure concentration of A. So this point then, our y-intercept point, is now ln, concentration of A at time 0. Our slope is still negative k. Okay, so let's write that. Y equals mx plus b. If we were to write this in y equals mx plus b formula, we would have ln of A at time 0 equals negative k t plus ln concentration of A at time 0. Okay. Oh, actually, I'm sorry. This should have been concentration of T. So that's at time T, sorry. And then here's your slope intercept, or there's your y-intercept right there. Okay, so if we rearrange this into point-slope form, we get ln of A at time T minus natural log of A at time 0 equals negative kt. And this equation is given to you on the AP equations sheet. So you don't need to memorize this one, but you do need to know how to use it. So this is going to be given to you. So anytime you have a graph of natural log of A versus time, natural log of the concentration of A versus time, and you see that that's a straight line, you know that reaction is going to be first order. So there is a special case of first order reactions called the half-life. So the half-life is the time at T 1/2. It takes for the reaction to reach half of its original concentration. So if you started at a 10 molar concentration, it's the time it takes to get to 5 molar. And then there's another half-life to get to 2.5 molar, and then another half-life to get to 1.25, and so on and so forth. So you can actually use the integrated rate law for this, and you can solve for T 1/2, given that the concentration of A is 1/2, because half the concentration by definition, and the concentration of A at time 0, that's 1/2, and then T is 1/2. So if you solve for this, you end up getting, and I'm not going to run through that whole derivation for you here, but you're getting that the half-life is equal to 0.693 over k. And this equation is also given to you on your AP equation sheet. You have a copy of that on the back of your periodic table. So you can double check that and make sure that you understand where to find everything. So this is given on the AP equation sheet. I want you to also notice here that there's nowhere in here that you have to take into account concentration. So the half-life does not depend on concentration. Does not depend on concentration. Okay, so there's your half-life case. Okay, moving on to our second order reaction here. So our second order reaction, we're going to consider that same reaction where we have A going into some products, and in this case, we're going to say it's a second order reaction. So again, as the concentration of A decreases, the rate or the slope also decreases. And again, just like in a first order reaction, as the rate slows down, so as rate gets slower, the slope gets smaller. And that means we get a curve. Okay, so just sketching this quickly here, so we don't know exactly what this curve is going to look like, but we get some kind of a curve there. So there's our sketch. Unlike the zero order reaction, again, just like before, the concentration versus time graph is not very useful because it's not a straight line. Not a straight line. Not useful for analysis. We can't use any of our equations here. Alright, for the second order reaction, however, we can manipulate this, and we get a linear relationship between the inverse and time. So for a second order reaction, we're going to be able to get a linear relationship between 1 over the concentration of A and time. So the slope here is still m, but it's slightly different because now the slope is just going to be m. It's going to be positive k. So I'm going to go ahead and sketch this. So this is going to end up looking something like this. So your m, or your slope, is going to be equal to positive k. And your intercept here, your y-intercept, is 1 over concentration of A at time 0. So our time is 0. This is 1 over A, so that's our y-intercept. So if we want to write this in y equals mx plus b format, so y equals mx plus b format, we would have our y is 1 over A equals positive kt plus 1 over A at time 0 for our intercept there. Okay, so rearranging that into point slope form, and point slope form is the form that you're always going to be given. So rearranging that, we get 1 over A at time t, I should have a t there, minus 1 over concentration of A at time 0, or your initial concentration, equals kt. So this equation is also given to you on your AP equation sheet, so there is no need to memorize this. So here, the rate is not negative k, so the rate is positive k. Okay, if you look on the bottom, there is a summary for you to look at where we have nicely summarized everything that we just went over in this section. So you have your rate laws here for your 0, first, and second order reactions, the concentration of A versus time, just when you graph pure concentration. Here's that integrated rate law. That's the one in point slope form, and this tells you which one is going to give you a straight line. Here's your slope, so negative k, and we can see the last one we just did was positive k. The straight line graph, so for 0 order, just concentration of A. First order, that was ln k, or of A, sorry. And then second order is the inverse, so 1 over the concentration of A is going to give you a straight line. But remember that that slope is reversed here. Here are your units of k for any given order reaction, and here's the half-life equation. Now the half-life equations for different orders are all given to you here. This is the one you're going to use most often for first order. Okay guys, that is it for video 2.2.1.